Hello and welcome to this video going through the walking talking mock for the high demand electric circuits questions. On question 6 now, so let's have a look what that's got to throw at us. So a student sets up the circuit shown in the diagram. The student uses the circuit to obtain the data needed to plot a current potential difference graph for a diode. Okay, so this is a diagram of the circuit. Draw in the boxes the circuit symbol for a diode and the circuit symbol for a variable resistor. Okay, so the diode is an interesting one because the diode is looks like that. Sometimes they have a window around them as well. Okay, that's absolutely fine. Sometimes the line goes straight through the middle, sometimes it doesn't. Oops, sorry, I'm trying to see it. Okay, so what you'll notice about the diode, first of all, is you can even see on the symbol here, look, on the diagram of it, it's non-symmetrical. And that's really important to always remember that, it's non-symmetrical. Okay, whereas lots of devices are symmetrical. This one here, it doesn't really matter, you can spin that around, it look pretty much the same. The diode deliberately got markings at a different one end to the other because it has a direction. Because of that, it always has, because of that, sort of, the symbol itself is non-symmetrical as well. A variable resistor. A variable resistor is a normal resistor, which is a rectangle, but anything that's variable has a large arrow drawn through it like that. Okay, and the arrow can go any direction you like, it doesn't matter. The student made 2 mistakes when setting up the circuit. What 2 mistakes did the student make? I love this question because it comes up really frequently. So whenever you get asked about any mistake setting up a circuit, without even looking, I haven't looked at the question now, but I can almost guarantee that one or both of the mistakes will be the ammeter or voltmeter connected in the wrong way. Okay, whenever this question gets asked, it's nearly always that. So let's have a look. Yep, there we go. The voltmeter is in series and it should be in parallel, and the ammeter is in parallel and it should be in series. The other thing you sometimes get is they'll have 2 cells and they'll be facing each other, so they'll be the wrong side, so you'll have a negative positive, then a positive, then a negative, and that will cancel each other out. But in this case, they've gone for the classic voltmeter and ammeter in the wrong way. The way to remember this is the voltmeter always goes last. Always. The circuit should work without the voltmeter. In fact, if I took this ammeter away right now, if I removed it, the circuit would, well, if that was an ammeter, the circuit would work. Okay, the ammeter here is in parallel, it's not essential to the circuit. When we draw voltmeters, I always teach students to draw them like that, to help remind them that they go in parallel, whereas an ammeter goes in series like that. Okay, so the two mistakes they've made, the voltmeter is in series and should be parallel, and the ammeter is in parallel and should be in series. The reason that's an issue is the ammeters are designed, ammeters in parallel should be in series. The reason that's an issue is the ammeters are designed to let everything through them with minimal sort of impact on the current itself. It wants to measure the current without really stopping the current. So it's got a very, very low resistance indeed. It's like trying to measure the current in a river. There's no point building a dam to measure the current because you'll stop the current. So you want something very, very low impact. So here the ammeter's got incredibly low current, low resistance. So what will happen is as the current comes through here, it will just all go around the ammeter and it will miss the diode entirely. So that would create a short circuit. Here, the voltmeter is the opposite. The voltmeter is designed to go in parallel and is designed for only one electron ideally to go into it, nothing else. Incredibly high resistance because it doesn't want to change, it doesn't want all the current to go through it, because it wants to compare the potential difference, the energy being carried by 1 coulomb of charge, 1 gang of electrons here, with how much energy is being carried by 1 gang here. So it wants to be incredibly high resistance. So if it's in series, it just stops the entire current going through. The most common mistake when students set up circuits as well. That's why, as I say, I always insist on students adding the voltmeter last of all. Once the circuit's working, then I allow them to touch voltmeters. Otherwise, it won't work. After correcting the circuit, the student obtained a set of data and plotted the graph below. Potential difference in volts, okay, current in amps. At what potential difference did the diode start to conduct an electric current? Okay, so the current is 0, 0, 0, 0, 0, 0. Oh, it goes there. So it starts to lift probably, so at 0.2 volts and above. Okay, so in fact 0.2 would be the answer there, wouldn't it? Use data from the graph. Oh, I love these questions. So I have to draw lines on the graph, from the graph. So use the graph to calculate, it's a calculate question, the resistance of the diode when the potential difference across it is 0.3 volts. So I've got to use data from the graph. So I'm looking at V is equal to 0.3 volts. I know that I'm going to have to use V equals IR because I need the resistance, which is R. The graph up here has got current, so it's got I. So at 0.3 volts, so let's see, so I want I at 0.3 volts, don't I? And I can calculate R. So 0.3 volts, I've got to use the graph. So the way I demonstrate I'm going to use the graph is I draw lines on it. And that shows the examiner that I'm using the graph. I'm deliberately doing mine in red because just to help you see it a little bit more clearly. Okay, so just by drawing that, I've probably got 1 mark for, or I have got 1 mark because I've used the graph. Now I've got to get data from it, so I've got to read this effectively. So 0.01 there, 1, 2, 3, 4, 5. So there's 5 steps between 0 and 0.1. So if that's 0. Let's just see, I can do 0.01 divided by 5, and that will tell me how big each step is. I'm going to do it on the calculator just to check. So 0.01 divided by 5 equals, hopefully I've changed this into some weird mode, non-mode, right, 0.01 divided by 5 equals, so each one is 0.002, and I've got 1, 2, 3, 4 of them, so times 4 is equal to, I is equal to 0.008 amps. Okay, that's a tricky one, that. Okay, it's a difficult graph to read, so you can see there how I've done it. I've deliberately worked out how big one block is, one little square, and I've just said, well, there's 4 of those little squares, so 4 times that gives me the value 0.0008. Okay, so V equals IR, so I'm going to put the values in before I rearrange it. 0.3 is equal to 0.008, being really careful not to make a mistake transposing it, so moving it from one place to another, which means R is equal to 0.3 divided by 0.008, gives me 0.3 divided by 0.008 equals, always make sure you change the decimal, 37.5. Now because this question hasn't asked me to do it in 2 sigma figures or anything else, the fact that I haven't got a huge long number, that convinces me I'm probably right, on the right tracks anyway. If I'd got a number there with to 10 decimal places and it didn't tell me in the question to round my answer, I've probably made a mistake. Equally, if it says to round your answer, I'm expecting a massive long number with many multiple places, many decimal places. So 37.5 ohms. The diagram shows the trace produced by an alternating current AC supply on an oscilloscope. Each horizontal division on the oscilloscope screen represents a time of 0.1 seconds. Calculate the frequency of the AC supply. Okay, so frequency. Frequency is time. Equals waves in 1 second. Okay, so number of waves in 1 second. T equals the time for one wave. So what we get is, if I know that if one wave takes 1 second, frequency 1, dead easy. If I know that one wave takes 2 seconds, then I'm going to get half a wave in 1 second, so frequency of half. If one wave takes a quarter of a second, I'm going to get a frequency of 4 waves in each second. So the first thing I want to do, and we end up with a relationship of, the formula we need is F is equal to 1 divided by T. Okay, so what I want to do here is I want to find the length of one wave. So let me just quickly work out where one wave is. So there's my centre line, my rest point along there. I've got peak. I've got one peak there, another peak here. So the distance from peak to peak, that's one entire wave. So one wave is there. I could go from trough to trough, or I could go from any point to the same point on the next wave, but peak to peak is a nice easy one. I know each square is 0.01 seconds. So 1, 2, 3, 4. So 4 waves. So T equals time for 1 second. Let me just put a line down there. So there we go. So time for one wave, I know it's 4 squares. 4 squares times 0.01 seconds equals 0.04 seconds. So one wave is 0.04 seconds. So the frequency is 1 divided by 0. Sorry, missing off the page. There we go. So 4 squares. I counted them across 1, 2, 3, 4. So 4 squares. Each square is 0.01 seconds. Gives the time for one wave of 0.04 seconds. I know that frequency is 1 divided by the time period. Okay, so the frequency is 1 divided by 0.04 equals 1 divided by 0.4 equals 25. Okay, so frequency of 25 Hertz. A diode is now connected in series with the AC power supply. Okay, so let's just, well, that's what it looks like. The diode there. There's the AC supply. So it comes through here, so don't worry too much about this yet, because this bit over here to the right is effectively the oscilloscope. Becomes a very, very fancy ammeter. And what we get is the AC supply, so the current is alternating forwards, backwards through the diode, through the resistor, and then it's being recorded over here on the oscilloscope. So the question is, why does the diode cause the trace on the oscilloscope screen to change? Okay, so why does it change? It's worth a total of, this one's worth, let me see how many marks, 2 marks. So 1, 2. Okay, so 2 marks. So we need to try and explain why this happens. So the first thing is to understand what's going on with the AC supply. The current changes direction, and the diode has really high, remember I said about the symbol for the diode, shaped like that, and normally, so it's a non-symmetrical symbol, which means its VI graph is non-symmetrical as well, so quite often it's like that. The VI graphs are the other symbols that you need to know, remember. A bulb, symmetrical and curved, means it looks like that. The resistor, symmetrical and straight, looks like that. That one's directly proportional. Okay, V against I. V against I. This one is curved because it gets hot as the current increases, as potential difference increases. So this one here, the first thing we need to know about diodes is diodes have very high resistance in one direction. Okay, that's what diodes do. They have very high resistance in one direction. Okay, so because it has a very high resistance in one direction, as AC supply changes current direction, diode will reduce current when it is in high resistance direction. Okay, so when it's in high resistance direction, so when the current is trying to be pushed down one direction, you don't get any current at all. So this here is I, and that's 0 there. Okay, I'm not sure if you've done that topic yet or not. If you haven't, don't worry, but I think you probably have actually. AC and DC. Yeah, so AC means that the current changes direction, whereas DC means the current's in the same direction always. Okay, hope that was useful. Take care. See you soon.